Let's do this example. What have I given you? Scalar function. I'm asking you to compute this, which is basically the work over the gradient vector field of that scalar function. Right? This is the work integral. That gradient f is our capital F. All right, who wants to tell me how to do this? I'm going to show you two different ways of doing this problem. All right? Here's the first way, option 1. I'm going to actually grind this answer out. Okay, so let's get the gradient of f. That's going to be my field, and the gradient of f here is 2x comma 2y. Pretty straightforward vector field, right? You remember how to do this? Gradient? Partial of that with respect to x, partial of that with respect to y. Yeah? Now, I need my path, right? I need my path, which is given, and I need the derivative of it to put here to dot with that field. So let's take the derivative of this. That derivative kind of sucks a little bit, doesn't it? It's just product rule, but it's not that bad, but it's not that great either. So derivative of that is going to be sine t plus t cosine t. And then the derivative of the second component is going to be cosine t minus t sine t. All right, that's my derivative. So I've got my field, right? My field has x and y in it, right? I need to evaluate this field at the x and y from the position. This is the x of the position, this is the y. So this becomes integral from 0 to pi, that's given to me. And then the field, f, right? The field, the gradient vector field, replacing x with what? With t sine t and y with t cosine t. So 2 t sine t, and then 2 t cosine t. And then I need to dot that still with this thing, sine t plus t cosine t, yuck, cosine t minus t sine t. Got to dot those. This is with respect to t. Any questions? Let's dot. Equals integral 0 to pi. All right, so these two multiplied together is going to give me 2t sine squared t plus 2t squared sine t cosine t. It's almost like I'm foiling, but not quite, right? It's just these two together, and then plus now these two together. Plus 2t cosine squared t, and then minus 2t squared cosine t sine t, or you could write it the other way around, dt. Yeah, we got a lot of nice things happen now. Y'all see all the nice things that happen?
Yep, the sine t cosine t is both cancelled.
These are gone, right? Those are gone. And then both of these have what in them? 2t. Factor out the 2t, and you're left with sine squared t plus cosine squared t, which is 1. So all of this becomes the integral from 0 to pi of what? 2t dt, which is t squared, evaluated from 0 to pi, which is pi squared. All right. That's option 1. Now, option 2. fundamental theorem of line integrals. I'm going to use that. Now, am I allowed to use it? Well, is this a conservative vector field? Mm-hmm. Right, it is, because it's the gradient of a scalar function. Right? So I don't actually have to do any of that work. All I have to do is take the scalar function, right? So this right here, this integral over the curve C of the gradient of f dot dr, that's just going to be equal to the scalar function evaluated at the endpoint of the curve minus the scalar function evaluated at the other endpoint, which is the starting point of the curve. That's it. That's all I have to do. So let's get the endpoints of the curve, right? I don't need any derivatives. I don't need to do any dots or anything. I just need to look at my curve, and this here is A, and this here is B. So what is the vector function at B? Well, that's the vector function at pi. What's the value of the vector function at pi? So let's plug pi in here. Pi times, what's sine of pi? 0, right? Sine of pi is 0, so that's 0. And then plug in pi here, times cosine of pi is -1, so just negative pi. So you get the vector 0, negative pi. Right? That's what I get when I plug in. Mm-hmm. Yeah? And now? We plug in the starting point, which is r of 0. And that's easy to plug in, right? Because it just kills everything, 0, 0. Okay. All right. So now let's go over here. This is f of r of pi minus f of r of 0. And then this becomes f, the scalar function evaluated at a vector. And this is what I talked to you in the past about. Like, the notation's weird. It doesn't seem like you should be able to plug a vector into the scalar function, but it's pretty straightforward. You see, I'm plugging that vector into the scalar function. And then over there, I'm plugging in the vector 0, 0. So when I say plug in the vector 0, negative pi into the scalar function, all I mean is replace x with 0 and y with negative pi into the original, into this. What is that? What happens if you do that? Plug 0 in there, boom, plus negative pi squared, right? That's what happens when you plug those into the scalar function. Then you subtract from that. Now let's plug in 0 up there, and that's just 0 squared, 0 squared plus 0 squared, which is 0. And all of it together? Pi squared, same answer. Which one do you think is easier? This one probably, right? Because all you had to know is the two endpoints of the curve. If you know the two endpoints of the curve, written as vectors, then you just plug those into the original scalar function. You never needed to take the gradient, right? Never needed to take the gradient. Never needed to take the derivative of the position function. Never needed to dot anything, right? None of that was necessary. We can only do that because it was a conservative vector field, right? You take out the conservative vector field, that's not allowed. Path independence. All right, what you're looking at here is what we call closed curve. Right? Seems logical. You start at a point, draw your curve, you come back, you end at the same point you started. That creates a closed curve. So you have both, with a closed curve, you have to have the same initial point and terminal point. So now the theorem. The work integral is path independent, meaning the answer you get from this does not depend on your path at all, right? If and only if the answer for the work is 0. Only if your work is 0. On every closed path, C in D. Okay. So this theorem says that if you're looking at the work over some curve C, then it's not going to matter what path you take at all. It's path independent. But that will only happen if the work is going to come out to be 0 in the end. So the only way to be path independent is if you can guarantee that the work's going to be 0. You can also read this theorem the other way around. If your work integral gives you 0, for every closed curve in there, in the space, then I guarantee that you have path independence. So it's like, all right, if you go and you have some curve, it's closed, and you compute the work there and you get 0, then it's path independent. Meaning that every closed path in here gives you 0. So it's hard to use this theorem, okay? It's really hard to use this theorem because you can't possibly test every closed curve in a path. It's impossible to do. But the good thing about this theorem is this. What if it's a conservative vector field? Then what? 0, right? Because we know we can say that the answer will be 0 always on a conservative vector field if this is closed. Why? Because the previous theorem, right, says that you just have to subtract the scalar function at the two endpoints. But if the two endpoints are the same, then you're going to get the same answer, and it's going to be 0 every time, right? But that only works with conservative vector fields. So that's what's in bold here is the big thing. So line integrals on closed paths of conservative vector fields are path independent. So if you're a conservative vector field, you're a closed path, then you're path independent. All right, that theorem is actually not going to be super useful to us for the rest of the way, but it's a theorem that the book mentions, so there it is. It's a result of the fundamental theorem of line integrals. Our bigger thing now is, can we figure out whether or not a field is conservative? Like if I give you a scalar function, right? If I give you this, if I give you f, then you can always calculate the gradient, and you know that's conservative by definition. So everything's going to be nice. But what if you have a field and you don't know where it came from? Can you figure out if it's conservative? And we did one example of this. Y'all wanted to see it. We did it. We did the partial integration. We're going to do a little bit more of it now. But before that, to determine if f is conservative, we first need to look at the definition of what means a simply connected region versus a non-simply connected region. So this right here, this region, is called simply connected. And that one is not simply connected. And I like to think of it this way. Inside that region, if I can draw a path like a rubber band, then imagine shrinking that path down. I could shrink the path down to a point. For any path I draw in here, I can shrink it down to a point. Another path, I could shrink it down to a point. But here, if I draw a path like this, could I shrink that down to a point? Sure, right? But does that work for every path in here? If I go this path that goes around that, if I try and shrink it, then I'm gonna have to leave the region, aren't I? So that is not a simply connected region. So when I continue with the rest of the notes and I'm talking about simply connected regions, this is what I'm talking about, not that. That changes things. Theorems don't hold the same if I have that situation.
How do you get a region like that? Does it feel like weird domain restrictions or something?
Yeah, I mean, just take a washer like that. There you go. It's not simply connected.
Right.
Yeah. All right. Now we establish what conditions must be held or met for a field to be conservative. It's a very, very simple check to tell whether or not a field is conservative. Very simple check if we're talking about two-dimensional vector fields. All right, so this only holds for two-dimensional vector fields. So let's say that somebody gives you the vector field right here. You have the p, which is the first component function. We'll call it p, and then q. No r because this is two-dimensional only. If you have a two-dimensional vector field, in order to determine if it's conservative, all you have to do is take the partial of this with respect to y and see if it equals the partial of that with respect to x. If those two are equal, then you have a conservative vector field. That's it. Now it may seem like why, right? You might be wondering why. Just wait, because we're going to talk about this in three-dimensional vector fields 2 sections from now, and you'll see that this is just a certain case from a more general idea. So I think it'll be easier to see it when we get to it later. For now, we're just going to take this and go with it. So look at that field right there. Is that a conservative vector field or not? Well, p is the first component function, right? This is p. This is q. The check that we have to do is this. I'm putting it off camera here. We have to take the partial of p with respect to y and ask ourselves, is that equal to the partial of q with respect to x? This is what we test for conservative. Check if it's conservative. That's the check we're making. So what is the partial of q with respect to x? Oh, sorry, I'm thinking of Green's theorem already. Partial of p with respect to y is what? 2x. What's the partial of q with respect to x? 2x. They're the same. It's a conservative vector field. Simple, right? Simple. Yes?
You mentioned earlier that it only works in 2 dimensions. Is there a more convoluted version for 3 dimension, or 3
There
dimensions
is.
just like?
There is, but we'll have to compute what's called the curl of the field. And then when you do the curl, that's going to require a cross product.
Oh.
And then we're going to have conditions on that cross product. It must be the 0 vector. So there will be a check. It's just not going to be as straightforward as that.
Okay.
Yeah. Now, since we know it's conservative, right? If we know it's conservative, then we know that it's the gradient of some scalar function. And so we just need to see if there's a way we can get it. And this is the example that we did already, but I'm going to do it again. All right? I don't know if this is the exact example, though. I don't think we did this one. Whoa. So is that a conservative vector field? We have to check that first, right? Is it conservative? So what is the partial of p with respect to y? Is this the same one or no? That is.
It's very different.
It's different? Okay, what's partial of p with respect to y? 2x. So we're taking derivative of this, right? This is p. This is q. So that's 2x. And what's the partial of q with respect to x?
2x.
2x. So they're the same, aren't they?
Mm-hmm.
Partial of that with respect to x is the partial of that with respect to y. So they're the same. So is it conservative? Yes, right? It's conservative. Now, if it's conservative, if so, find the potential function. So find that scalar function that generates that field. So here's where we have to go back and remember then that what we're saying is that the field we're looking at is the gradient of some scalar function, which by definition is the vector given by these components. The partial of the scalar function with respect to x, partial of scalar function with respect to y, right? We know that this is true. The field we have is conservative, so that means it's the gradient of some scalar, which by definition is this. So now what I'm going to do is I'm going to say, all right, well, I know that this has to match that, right? And this has to match that then. I'm going to start with that first one. I know that the partial of f with respect to x has to be 1 plus 2xy plus the natural log of x. I know that much for sure. Anyone remember what I did now? Antiderivative. We're trying to find little f, right? Ultimately, we want to know what little f is, right? We want to know what the potential function is. So we know what its partial with respect to x is. So to go back to f, we have to take the antiderivative on both sides of that equation with respect to what variable? X. So I do the integral of the partial of f with respect to x equals the integral the integral of 1 plus 2xy plus natural log x with respect to x. The left side is just what? Little f, right? And then this side is x plus x squared y. Antiderivative of 1 is x. Antiderivative of this, the y is a constant, comes to the right. Antiderivative of 2x is x squared. Plus, oh crap, what's the antiderivative of natural log x? X ln x minus x. Now, that one is one that the further you go along, the sooner you have that memorized, the better. Because it just comes up a lot. I mean, we all know derivative, that's 1 over x, but the antiderivative, it comes up enough that... How would you do that if you didn't know that and you didn't have the formula? By parts. Integration. It's an integration by parts. But we will not do that. That's our antiderivative, right? So far, almost. We're not done. I've done the antiderivative of this, this, and this. Now, this is where I told y'all, plus c is what we normally would say, right? But there could be some y's in there, right? There could be some y's in there that when I differentiated with respect to x would have gone to 0. So I'm going to say that this is more than just possibly a constant. It's some function of y. So I'm going to call it h of y, okay? H of y, some function of y.
Can we do g instead?
You want to use g?
What we use in diffie.
Okay, you want to use g?
Sounds weird.
Okay, that's fine. I'll use g. All right, good? Now, what I'm going to do is, I know what f is, right? I'm looking for f. I know f within some function of y. If I'm off by some y's and maybe some numbers. So now what I'm going to do is use the second part, that this partial with respect to y has to be x squared. So I'm going to differentiate this with respect to y. And then I'm going to set it equal to that. So, but partial of f with respect to y must be, let's see, 0. And then that's just x squared. All of that's, oh, you know what? I just realized that these x's canceled. Those are gone. I don't need those there, right? X minus x, that could have gone away a long time ago. That's the partial of that with respect to y. And then what's the derivative of this with respect to y? G prime y, right? Or the derivative of this with respect to y. I don't know what that answer is. So you can use different notations. I can use g prime y, or I could use some other, I'm going to use this notation, g subscript y. That's letting you know that I took the derivative of that with respect to y. I don't want to use prime because prime doesn't tell you what you're differentiating with respect to, right? So if we have more than if we have like 3 variables, we're going to have to keep track of what we're differentiating with respect to. So, good? But this is this, which implies that this must be equal to what? What is that? Right? Because remember, this is this, right? Has to be equal to that, right? X squared. So that implies that x squared plus the partial g with respect to y must be x squared. I'm setting those equal to each other. I'm setting this equal to that up there. And what does that force g, partial g with respect to y to be? 0. So the partial of g with respect to y must be 0. And now I can tell you what g is by taking the antiderivative of that with respect to y, which should be a constant. And it won't have x's in it, and it won't have y's in it, for sure. So the integral of the partial of g with respect to y equals the integral of 0 with respect to y. So this is just g of y equals some constant. So I'm ready for a final answer. my potential function. The potential function is the one that creates the conservative vector field. My potential function f is equal to, it was x squared y plus x ln x plus any constant. So I could put 0 there if I want, or I could put 1 or 2 or whatever I want. There it is. You can check your answer, can't you? If I take the gradient of this, I should get that field. Questions? Sure? All right. I'm guessing by the look on your face that this is familiar enough that you're happy.
We just did an exam on those things.
Oh, okay.
That's why we said, can we do?
Oh, good. Yeah, yeah. So what about the next example? This is an important problem because we're going to put a lot of ideas together here. I want us to compute the work, right? I want us to compute work. I want us to compute work. I give you a field, right? I give you a curve, limits on the curve, right? So let's just act for a moment as if we don't really care and we're just a student that just likes to grind things out, right? And we're just going to say, all right, I'm going to do this. So what I'm going to do now is I'm going to take my curve and I'm going to come over here. T is restricted between 2 and 1. And so I know for this formula, I'm going to need the derivative of that, right? So I take its derivative, which is going to be 2t1. There's my derivative. And now I can set this integral up. It's going to be the integral from 1 to 2. And then it's going to be the field. I'm given that field, right? But what am I going to do with the field? Everywhere I see x, replace it with t squared plus 1. And everywhere I see y, I'm going to replace it with t plus 2. OK, so 1 plus 2 times x, t squared plus 1, and then times y, which is t plus 2. And then, still going, right? Plus natural log of t squared plus 1. That's just the first part, right? That's just this right here. Comma, x squared, so t squared plus 1, that squared. That is my field evaluated on that curve, right? Dot that with 2t1 dt. No, right? So you're looking at it, you're like, okay, I know what I need to do now, and it's doable, right? But it's going to be a lot, well, I don't even know, maybe, hopefully the integrals are doable. But can you imagine now just investing the time and energy to do that? Whereas if you realize that that field is conservative, right? It's conservative. You could have checked that in the very beginning, right? That's the example we've been working with, that field. It's conservative. We found its potential function. It didn't take us too long, right, to get the potential function. So what I can tell you is that instead of doing all that, I have a conservative vector field, which means the fundamental theorem of line integrals counts, right? I mean, fundamental theorem of line integrals, along with the fact that it's conservative, means that there's path independence here. So I just need to evaluate the scalar function at the two endpoints of the curve. So this right here, screw all this, right? I'm just going to say this will be the scalar function evaluated at R of B minus the scalar function evaluated at R of A. Fundamental theorem of line integrals. Now, I still do have to figure out what R of B is and what R of A is, and then plug those in.
We also have to figure out what f is.
We did. That was our previous example.
Yeah, but.
Yeah. Yes, you would have to do that as well. Yeah. So let's figure out what R of B is. That's R of 2, right? So R of 2, plug 2 in, what do you get? 5, 4. And then you plug in 1. Plug 1 into that, you should get 1, 3. Right? F of B. R of B, R of A, right? Those are my two endpoints for my curve, written as vectors. Oh yeah, I don't know why I put 1, 3. Thank you. 2, 3. I don't know. All right, we need to know what F is. We did that just a minute ago. F was it was x squared y plus x ln x plus c, right? And I can use any constant I want. So I'm going to use 0 because it's just easiest to work with, right? So there's my scalar. So what I need to do now is I need to plug in. We're going to come over here. We're going to go into that function. We're going to plug in this for x, that for y, right? And then we're going to do this for x, that for y, subtract the answers. So continuing right here. All right, if I plug in to that function, for x I'm replacing it with 5, and the y is 4. So 5 squared, 25 times 4 is 100, minus, and then here I put a 5 and a 5, so 5 ln 5. And then I'm going to plug, yeah, I don't know why I put minus. And now we go to this one now, right? And it's going to be 2 squared, 4 times 3 is 12. Plus, and then 3 is going to go on, or no, 2 is in for x. So 2 ln 2. And that's some number, and that's our answer. Questions? No? We have not seen what it takes to show that a vector field in three-dimensional space is conservative. Curl thing I was talking about a minute ago. We haven't shown that yet. But we can still try to see if it's conservative by seeing if we can come up with a potential function. So we're going to do more of what you just liked, except that now we have 3 components instead of 2. So the question here is f the gradient of some scalar function, right? Is it? I don't know. Let's assume it is, okay? Let's assume it is. If it is, then we have this, that the field is equal to